In this last numerical part of the example, we're going to take the member end displacements that we calculated and turn them into, using the slope-deflection equations, the member end moments. Now what I'm going to do here is we're going to put the numbers in that we've calculated by hand, and then I'm going to talk a little bit about what happens as a rounding errors and how do you anticipate whether it's a rounding error or some other kind of mistake, and show you, a couple of things in that kind of regard. And so, for instance, let's put in there the displacement that we've got here, the ek theta b business. So that'll be 6 times minus 7.78 minus 72 minus 166.7. Now, earlier I had said something about, hey, are those units really kilonewton meters? Well, they have to be, right? Because this is really a moment term. We've got moments here. If we were very careful about everything that we were doing, we would see that those are kilonewton meters all the way through, right? And if you plug that in, we got 6 times that minus the 72 minus the 166, which is really a repeating 6/7, we get a minus then 285.34, right? And if you carry out more digits, you'll actually get a 311 out here instead of the 347, it turns out. And that's obviously quite close and certainly good enough. Then let's do 12 times minus 7.78 minus the 72 plus the 166.7, and there we get the 12 times that minus the 72 minus the 1, well, not minus, but rather plus, and you get 1.34 positive. Now, I actually get, when I carry out a lot more digits and everything, I get 1.38 rounded in reality, just like we had the 11 before. And again, that seems pretty decent. Why am I fussing around with this? Well, let's look at 16 times minus 7.78 plus the 8 times the 7.37 plus the 64, and you're going to get, just straight out of that math, oops, something's not right there. 16 times that plus 8 times 7.37 plus, there we go, plus 64, and you get a minus 1.52. Well, that seems like maybe not a big deal, but notice something here, that these two should sum to equal 0, and that's not going to. It's a little bit off. Percentage-wise of what we have here, that's a lot off. If the numbers were much bigger, I wouldn't be so concerned about it at all, and I'm not really concerned here, but it is a numerical error. It's a little bit different. So those two should really be equal and opposite, and again, if you carry out more digits here, you get a negative 1.38, and it'll work out much better. So it's all about right now that what we did to get here, and we wouldn't have even really seen it at the larger magnitudes of the moments. This is obviously a very small moment. We'll talk about that in just a little, in another part here. We'll talk about that. And then we get 8 times the minus 7.78 plus 16 times 7.37 plus the 64, and then again, let's work that out. 8 times that, which is negative, plus the 16 times the 7.37 plus the 64. And those of you following along at home and punching in your own numbers probably already know where that rounding error came from. It's probably something I was a little sloppy about when I was doing my own rounding. We get a 0.7 there. And one reason I actually am a little fussy with this is when we go to do the shear and moment diagrams, the small little change we have here may cause us to have a little bit of closure problems on the the moment diagram, we could probably make the shear work out fine, but we'll end up with just a slight little problem when it comes later on. And that's where you have to have a feeling of, well, if I have a complicated situation, did I just mess that up, or is that really just a rounding error issue? And we get the last one. Oops, 12 times. That's probably what I did that other time, was a plus instead of a multiplication. Minus the 208.3, and we get a minus 119 point. See, that gets rounded up to 9, and that starts to say, hey, it's supposed to be the same. And again, if you do it with more digits, that will be a lot better ultimately. And then the last one, and 6 times 7.37 plus the 208.3, and we get the a positive 252.5, and you would get, with more accuracy, 252.6. So let me fix something back up here, just to be consistent in formatting. And that is about 3.5 or so, and then what I really would get is 285.31 if I were to carry all that. So the red means more digits, the green means, or it might look black to you, rounded values. Alright, let's take those and put them on the free-body diagram, and in another part we will then go and actually look at, another part we will look at doing the actual shear moment diagrams and everything else. But there's a lot going on here, so let's see. We've got then for MIB a negative 285.3, so that means that it is opposite of clockwise. So 285.3. I'll go ahead and start allowing rounding errors to happen a little bit here. We have a positive 1.4 on that end. On this end we get a negative, or a frowny face ultimately, counterclockwise, also 1.4. At the far end we get a clockwise or positive, but that becomes frowny face on the other end at 119.8, and then we get a 119.8 on the end of that member, and we have then finally 256 or 252.6 on that end. We've got shears that have to get done in here. I'm not going to show them the way they're going to act yet. We'll do that in the next part. And before we close off this video and get to the next final part, then I'm just going to show the free body diagram of the joint briefly, because we have a reaction sitting in here, and we've got then shears that will get flipped from there, and we'll have then these moments that will come into play, and we'll address all that in the next segment.